Okay, we're skipping chapter 9, which is about differential equations, because most of you will have to take a whole semester on differential equations at some point soon. They are very, very useful, but we're not going to do them in this class. What we are going to talk about are a couple of different ways of representing graphs and doing calculus with those curves. The first we're going to talk about is parametric equations. Those of you who have done physics were probably familiar with a lot of this stuff, but here's the idea. The idea is, normally we've been dealing with equations written as y equals some function of x, and the graph of an equation like that can look lots of different ways, but any way you have an equation y equals a function of x, it will pass the vertical line test. That is, no vertical line can hit it twice. Sometimes instead of y equals a function of x, we'll have x equals a function of y, and those graphs can look very different, but instead of the vertical line test, they have to pass the horizontal line test. No horizontal line can hit a graph like this twice. But there are some graphs that we would like to deal with that don't pass either test. Okay, here's a graph that's got these loop-de-loops and so forth going on in it. That curve is not a function of x, and it's also not a function of y, because it doesn't pass the vertical line test and it doesn't pass the horizontal line test. So we would still like to be able to do calculus with a graph like this. That is, we'd like to be able to do things like find areas in different sections of it, or find the lengths of the curve, or find the slope of a tangent line at a point, those kinds of things, but we need a function to be able to do calculus. All of calculus has to do with rates of change of functions and integrals of functions, and this isn't a function of x or y. So what we do is we think of graphs like that as we interpret them as the path of some object or particle moving across the plane. So instead of thinking of the curve as just a static thing that's there, we think of it as something that's being traced out over time by an object. Just like when I drew it with the tip of my, well, in this case, the tip of my stylus, but anyway, usually the tip of my pen or pencil moving across the paper through time. Well, if it's like that, then the horizontal position of my stylus and the vertical position of my stylus are both functions of time. So I can write the x-coordinate as a function of time and the y-coordinate as a different function of time. And what I have is a system of parametric equations, or just sometimes we say parametric equations for the curve, with the parameter being time, or t. Okay, so these are parametric equations parametrized by t. T is the parameter, that is, t is the one independent variable, and then there are two dependent variables. X depends on t, and y also depends on t separately. Okay, with this, we can have any kind of strange path in the plane we want. Now, we think of this usually as the path of a particle moving through the plane. You don't have to think of t as a time variable. You can think of it as something else, and you can think of this instead of the path of an object moving. You can think of it other different ways, but that's the most common way to conceptualize it. Okay, so for example, what would happen if I had the parametric equations x equals t squared and y equals t squared? What path in the plane do I get if x is time squared and y is time squared? Well, first of all, notice that in this particular example, x and y are always equal to each other. So the path is on the line x equals y, the diagonal line there with slope 1. However, it's not the whole line, because t squared can't be negative. So x and y can't be negative. X and y both are 0 or greater. They're 0 if t equals 0, and if t is not 0, then x and y are bigger than 0. So that means I only have part of the line. Now if I think about different values for t, if t is negative, I might get some points like this. Bigger negative numbers put me farther away from the origin, and then as t gets closer to 0, the t squared value gets closer to 0, so x and y get closer and closer to the origin. When t hits 0, I'm at the origin, and then as t increases some more, moving away from 0, x and y will move away from the origin. So I get this ray, and if t can be anything, then for negative t values I'm headed towards the origin, and for positive t values I start heading away from the origin. Sometimes we restrict the t values, so if, for example, we specified that t had to be greater than or equal to 0, then the path would start at t equals 0, which is the point x equals 0, y equals 0, and it would move up and to the right faster and faster and faster, because as t increases, t squared increases even faster. So we'd start at the origin and move up and to the right with increasing speed. When we graph parametric curves, because we're thinking of these as paths of objects moving through time, we usually indicate which direction the object is traveling along the curve. That is, as t gets bigger, which way do the points go? And we indicate that with an arrow. Here's another example. Here's a system of parametric equations, x equals t plus 1 and y equals 2 minus t. And this time I'm going to specify that t is in the interval from t equals 3 to t equals 5. Okay, what does that graph look like? Well, the easiest way to graph parametric equations is to make a table of values. T can be 3 or 4 or 5, or anything in between. So if 3, 4, and 5 isn't enough information for me to figure out what the graph looks like, I could put in 3.5 for t and 4.5 and any more I want. But 3, 4, and 5 will be enough here. Then I plug in, if t is 3, x is t plus 1, so x is 4, and y is 2 minus t, so 2 minus 3, that's negative 1. Get down, cat. Okay, and then the same thing, plug in t equals 4 and t equals 5, and you get some x and y coordinates. Those x and y coordinates tell me points on the graph. So let me mark out some scale on the axes here. At t equals 3, I have the point 4, comma, negative 1. That's there. At t equals 4, I have the point 5, comma, negative 2. And then I also have the point 6, comma, negative 3. And that's the end. So the path goes from 4, negative 1, through 5, negative 2, and stops at 6, negative 3. As t increases, I'm moving from 4, negative 1 down and to the right. So I indicate that direction with an arrow. And then just some vocabulary, so that's the graph. And then just some vocabulary. The vocabulary is that point where we started, the smallest t value, in this case t equals 3. When you plug that in and you get x, y coordinates, that point is called the initial point of the curve, or of the graph. And the ending point, that is, where do you stop, the largest value of t, in this case 6, comma, negative 3, that's called the terminal point. Okay, so the initial point and the terminal point are some vocabulary that may come up. Now, there's another way I could have figured out what the graph of this looks like. With this particular system of parametric equations, I could have done what's called eliminating the parameter. That is, you pick one of the equations and solve it for t, and then substitute that into the other equation. So if I take the x equation and solve it for t, I get t equals x minus 1. I plug that into the other one, and I get y equals 2 minus t becomes y equals 2 minus x minus 1. Simplify a bit, and I have y equals negative x plus 3. So x equals t plus 1, y equals 2 minus t is a path on the line y equals negative x plus 3 that has slope negative 1 and y-intercept 3, right? But notice that when I do that, when I eliminate the parameter, I lose some information. I lose the information about which direction my object is traveling, the particle is traveling, right? It doesn't tell us direction of travel. And if a certain t interval was specified, like it was in this example, from 3 to 5, I've lost that information as well. I don't know which segment of the line the parametric equations were going to give me for those specified t values. But it does help you sort of visualize what the path will look like, because we are much more familiar with interpreting things like y equals negative x plus 3 than we are familiar with interpreting x equals t plus 1, comma, y equals 2 minus t. So in class we'll see some more examples, and then the next section will be, okay, now we know how to use parametric equations, let's do some calculus. I'll see you guys in class.